So today in Chapter 5, Section 4, guys, we're going to focus on isosceles and equilateral triangles. In 5.3, we focused on proving triangles congruent using side angle side. It was like a shortcut. And we're going to talk more about other shortcuts in subsequent sections. But before we get into those, we also want to utilize certain theorems and corollaries and stuff that relate specifically to isosceles and equilateral triangles so that we can find some missing information, okay, in our triangles, and we can use them then along with the shortcuts that I gave you yesterday and I'm going to be giving you in the future. So again, first we got to talk about specifically isosceles triangle and how we name the parts, right? We know that the sides are called segments in a normal triangle. They're made up of line segments. We know there's 3 angles. We know the angles each have a vertices. But when it comes to an isosceles triangle, we sort of give a little bit different names to things. So the bottom side of the triangle, or remember, in an isosceles triangle, 2 sides are always going to be equal, right? So, for example, the 2 sides that are equal, we call them the legs. Okay, the unequal side, we call it the base. And the base is not always at the bottom. This could be flipped over and it would still be the base. It just wouldn't be at the bottom. So again, the base is always the side that has a different length than the other 2. The 2 equal sides called legs. The vertex angle is the angle that is created when the 2 equal sides connect at that vertex. Okay, so that vertex angle is made up of the 2 equal legs, okay? And then the base angles are the angles that are formed down here, okay, where the equal legs hit the base. So the legs hit the base, that's the base angles, and where the 2 legs meet, that's the vertex angle. Now, in an isosceles triangle, the base angles are going to always be equal to each other, okay? And we'll talk about that a little bit later. But again, this is a lot of memorization because we're going to give you problems where we're going to describe an isosceles triangle. We're going to tell you the length of the base or the length of a leg. We're going to refer to the base angle, and you kind of have to know which one, or you definitely have to know which one we're talking about. You have to be able to draw this out on your own. So there's a theorem that goes with the base angles, okay, and it's called base angles theorem. And it says if 2 sides of a triangle are congruent, so again, this means if it's an isosceles triangle, right? Then the angles opposite those sides are congruent. So what happens is here we're looking at this triangle. You see the 2 legs, right? Here are AB and AC. Those are the equal sides. Notice the tick marks. This leg here equals this leg here. Well, we know in our mind then that this is the base, and we know that these are the base angles, okay? And what happens is when the legs are equal, the base angles are congruent as well, okay? So the sides, the angles opposite those sides are going to be congruent. And that's what it's telling you. So if 2 sides of a triangle are congruent, then the angles opposite them are congruent. So if AB is congruent to AC, then angle B must equal or be congruent to angle C. Now, the converse of this is the other way around. What if I were to give you a triangle and I would tell you that these 2 base angles, these 2 angles down here are equal? Now you can do it backwards, and we can say if the 2 angles of a triangle are congruent, then the sides opposite those 2 angles must also be congruent. So again, in the regular base angles theorem, you're given that the sides are equal and your conclusion is that the angles are equal. In the converse, you're given that the angles are equal and your conclusion is that the sides are equal. Okay? And so you're concluding 2 different things, even though in the end, all of it ends up being the same. Now, there's some corollaries that will flow from this, okay? And again, remember, corollaries are things that follow theorems. They don't really need to be proven much. They're pretty obvious, and they kind of are just shortcuts. It says, a corollary to the base angles theorem is that if a triangle is equilateral, meaning all the sides are equal, then it is equiangular. So if all my sides are equal, I know that all the angles opposite those sides are going to be equal. And then again, the corollary to that, and again, this is really long, corollary to converse, it's a lot. This is saying if all my angles are equal, then all my sides are equal. So the top one says, if I have these things in black, I can conclude then that all these angles opposite these equal sides are going to be equal. Okay, so my conclusion here is that the angles are all equal. And when I do the second one, it basically says I'm starting with the blue part. I'm starting with all the angles being equal, and then I can conclude that my sides opposite those angles are also equal. So this would be my conclusion. Again, in the end, it means the same. In the same shape, equal angles are going to be opposite equal sides, and equal sides are going to be opposite equal angles. So let's apply it and see, how this makes sense, or if it doesn't make sense, right? First of all, when I see this triangle here and in A, I see that this leg, let me do it with the other color. This leg here is equal to this leg here. So just to refresh my vocabulary, I know that those in green are the legs. I know this side here is my base. I know that this 30-degree angle is called my vertex angle. And I know that these down here are my base angles, okay? And what I know is because this is isosceles, I know that these two angles here, the ones opposite the equal legs or the equal sides, those angles are going to be equal to each other. So if I ask you to solve it, again, the three angles of a triangle add up to 180 degrees. So I've got a 30-degree angle, I have an angle that's x, and I know this one is also x, because remember, my base angles are going to be congruent here. And I've got x. So I've got 30 plus x has to add up to 180. So 30 plus 2x must be 180. I'm going to subtract 30 from both sides, and I'm going to get that 2x equals 150. And when I divide by 2, I'm going to get that x equals 75 degrees. So when it asks me for the value of x, in this case, it's 75. And again, I would make sure now. So if this is 75 and this one's 75, right? 75 and 75 is 150. 150 and 30 is 180. And yeah, it makes sense. So x is 75. When I go to B, I notice that here they're giving me line segments, and they've given me some equal angles. And so notice that this angle here and this angle here are equal. Well, if my angles are equal, I know the sides opposite those angles are also going to be congruent. Okay, so I know here, now I'm looking at this, I know that my legs of this triangle are these two sides because they're equal. My base is going to be this one. So we're talking about an isosceles triangle here. My base angles were those two equal angles, and the legs are the sides. And so, again, I know that my legs are equal. So my setup here is going to be 2x minus 4 has to equal x plus 5, because those two green legs or sides have to be equal. So I'll subtract x from both sides. X minus 4 is 5. I'll add 4 to each side, and I'll get that x equals 9. So in this problem, all they wanted me to do was solve for x. So x is 9. If they wanted to know the measures of the side lengths, I would have to plug x in and find each individual side. Okay, and then I go to C, and again, I'm looking to see what did they give me here. And in C, I have an angle that's 56, okay? I have a side opposite that angle that's 41. I have this angle that's 62, and I have the side opposite that. And it makes sense that my sides don't equal each other, because if my angles aren't equal, my sides aren't going to be equal. So right now, this is all I have, and I might feel like I'm stuck. But I do know what I need to do to find this third angle here that I don't know what the measure is. I know that 56 plus 62 plus, let's call this y, okay, plus y has to equal 180 degrees. I'm going to do my math here. I get 118 plus y equals 180, and y equals 180 minus 118, and y equals 62. So once I do the math, I realize that the angle here is 62. So now notice what I've got here. I've got an angle here that's 62 and an angle here that's 62. So remember, the sides opposite the equal angles are going to be equal. So if this side is 42, then x has to also be 42. And so what my shape ends up being is it's an isosceles triangle again, and these ended up being my legs. This ended up being my base. So my base angles were both 62, and my legs were equal, and they were 42. So x is 42 in this problem. So again, you have to apply the skill differently, whether you're talking about sides, whether you're talking about base angles, whether you're talking about vertex angles. There's a lot to do here. And then now they give us a proof, basically, and they want us to prove something here, and they give us the reasons, and we have to order these in the proper order. So I know this is a little bit challenging. I mean, I will tell you, though, let's just pretend we were doing our proof here, our statements, right? And our reasons, right? But basically, the given is angle 1 is congruent to angle 2. Well, that's D. So guess what? That's going to go first. Okay, because remember, we always start with our givens. So angle 1 is congruent to angle 2. Then they want us to prove this. Well, there's 4 steps here. So I know I'm going to have, a second step here, a third step here, and my last step is going to be what they want me to prove. So I know my last step is going to be that OK is congruent to OJ. So this one's out and this one's out. So now I just have to figure out, well, what 2 am I going to put in? So again, if angle 1 equals angle 2, now let me look at my drawing. Here's 1 and here's 2. Prove that line segment, they want me to prove that line segment OK is congruent to OJ. Well, I know that if I can prove that angle 3 and angle 4 are equal, I would be able to prove that their opposite sides, the sides opposite them, are equal. So that's going to be my goal, is to prove that 3 and 4 are equal to each other. So how do I do that? Well, first of all, I think that I can prove that 1 and 3, right? Angle 1 is congruent to angle 3, and I can prove that angle 2 is congruent to angle 4. Now, the reason they're not asking me for it, but I know that's vertical angles theorem, right? So that would probably be my next thing, which would be B. And then I have to find a way, right? If I know that this is equal, those 2 are equal, and I know that these 2 are equal, I have to find a way to know that they're equal to each other. So using substitution or transitive property, I can get to A, which says that angle 3 is congruent to angle 4. And so this would be the proper order for this proof. Okay, and you might say, well, how does that work? Well, I know, for example, if 1 equals 3, or here, for example, 1 and 2 are equal. So if 1 and 2 are equal, then I know that 1 and 4 are equal. I know 1 and 3 are equal, so I could sub 3 in for 1, and I know that 3 and 4 are equal. So there's different ways of doing it. They kind of shortened it a little bit too much for my taste. But bottom line is, through a series of a few steps in a proof, you would be able to prove that relationship. And that's how we would get to the fact that 3 and 4 are equal. And then they would therefore form your base angles. And we would be able to prove that those opposite sides, in fact, are congruent. And then the last one is here, a proof that we're going to do on our own from the beginning. And these are the ones I like the best because, again, here we can use our own logic. We can create our own statements and our own reasons. And if some of us want to use more steps, which is usually what I like to do, we're not confined to just 3 or 4 steps. So again, I'm always going to start with my givens. So M is the midpoint, right, of AB. That's going to be given. And the second thing that I'm given is the measure of angle 1 is equal to the measure of angle 2. That's also given. Now, as soon as somebody tells me, so I give me these things, I know that, okay, M is the midpoint here of AB. Here's B, here's A. Well, if M is the midpoint, I'm able to immediately know that line segment AM is going to equal line segment AB. And so for me, that's the next thing I'm going to do. I'm going to say AM is congruent to MB. And the reason I know that they're equal, and that's just the definition of a midpoint. So as soon as they tell me something's the midpoint, I'm going to use the definition to tell what's equal. The second thing that I know, when they tell me that the measure of angle 1 equals the measure of angle 2, I'm going to come over to my drawing and I'm going to kind of mark that. And as soon as I see, oh, angle 1 and 2 are congruent, I remember what I just learned. That means that the sides opposite those must also be congruent. So I know then that segment AC has to equal AM. So I'm going to write that. So AC is congruent to AM. Now again, what did I learn? What theorem or postulate or corollary told me that if the base angles were congruent, the sides opposite those angles were congruent? And that would be the converse to the base angles theorem. The base angles theorem says if the sides are equal, the base angles are equal. The converse says if the base angles are equal, the sides are equal. So base angles theorem. So again, now I've got that written down. Now, ultimately, what they want me to prove is that AC is congruent to MB. Well, I just proved it. If AC equals AM and AM equals MB, then AC equals MB. So I know that AC is equal to MB. And the reason would be I could do substitution or transitive property. But either way, I'm going to be able to prove it. So it took a few steps, but I was able to do it. And again, you might find a different way, but I think this is probably the most efficient way to do this proof.